The overall goal and purpose of this project is to find targets that are placed randomly in a randomly shaped arena and move them outside the arena. The first rover should map out the arena and communicate the location of targets to the second rover. The second rover should traverse the arena while avoiding obstacles and move the targets outside the arena. The overall system design of this project is split up into 4 different modules. The target locator and the searcher mover are on the first rover, and the Pathfinder and the target grabber are on the second rover.
The searching movement module is responsible for moving within the arena such that the target locator module can map out to obstacles and targets. This module only has one sensor for detecting the edges of the arena, and nothing else to see its surroundings. The sensor used in our project is the QTR-8A, which is an array of 8 analog IR sensors. Wheel encoders are used for calculating the rover's location and orientation. To ensure the rover actually goes straight, we used a PID controller which uses the right motor speed as a set point for the left motor. Every 10 milliseconds, both motors' speeds are compared and the pulse width of the left motor is adjusted so its speed matches the right. The equations used for calculating displacement are shown below. The number of wheel encoder ticks in a certain time period, divided by 2 constants, will simply result in the distance traveled or angles turned. This is the GUI for a Qt client used for displaying and controlling everything related to the searching movement of rover 1. The user can set the rover's mode of operation to either debug or random. Debug mode allows the user to manually input fine movements such as forward 10 cm or rotate 90 degrees. Random mode is the algorithm that the rover actually uses to map the arena. The top right area of the window shows the rover's movement information. There's position, orientation, action, and amount. Below that are the elements used to display the rover's current line sensor readings. The bottom right corner of the GUI controls the client's output of simulated data from the target locator. The first tab of the GUI shows all the inputs the user can send to the rover, including vertices, initial position, and number of targets. The client is also capable of sending corrected positions and different line sensor thresholds on the fly. This allows the rover to be more robust because it does not need to be reprogrammed to accommodate different surfaces or lighting. The algorithm used for mapping the arena utilizes random turns at random angles. This is to ensure the rover does not get stuck in a region of the map due to repetitive and predictable behavior. The rover initially moves forward in a straight line while requesting sensor data from the target locating module. Once the sensors indicate that an obstacle is 15 centimeters away, the rover stops. Then it picks a random direction to turn and rotates a random number of degrees. When the rover encounters the edge of the arena, the rover stops, inches backwards, rotates randomly again, and then continues to move forward. The algorithm repeats until all the targets are mapped by the target locator module.
The target locator module is responsible for mapping out the arena and ensuring that the searcher mover module avoids hitting any obstacles and targets. This module has 3 mid-range sharp IR sensors, which have a range from 7 to 30 centimeters, and 4 long-range sharp IR sensors, which have a range of 20 to 35 centimeters. The arrangement of sensors are shown on the right-hand side. The mid-range sensors are used in correspondence with the long-range sensors to account for the 20 centimeter blind spot of the long-range sensor. The target locator module will communicate with both the searcher mover and the Pathfinder module. This module will tell the searcher mover when there is an object that is within 15 centimeters in front of it, and will tell the Pathfinder the location of potential targets. The algorithm utilized to map out the arena is called histogramic in-motion mapping. This algorithm assumes a known location and orientation. It utilizes an occupancy grid that is represented as a 2D array that corresponds to the arena. The grid is interpreted in such a way that a really large negative value corresponds to a free cell, and that a really large positive value corresponds to an occupied cell. Each cell is initially assumed to be free. If we take a look at the picture on the right-hand side, we can kind of see how this algorithm works. Let's assume that we place a sensor at location C0, and that the distance that the sensor was read is distance D, and the corresponding distance point is point CC. This algorithm will perform a ray trace from point C0 to CC, and will decrement each cell on the line and increment the cell at the distance location with the larger value. Thus, over multiple iterations, the occupancy grid will start forming regions of cells that have a very large value, and this can be interpreted using the algorithm that I will describe next. The next step to this algorithm is to interpret the occupancy grid. This is done with a simple n-squared algorithm that iteratively looks through each cell in the grid and performs the following tests. Is this cell above a predetermined threshold? And is this cell at least 10 centimeters away from all of the other points that we have already added to our potential list of targets? And if these two tests are passed, then we add the position that we're checking at this current iteration to our list, and we continue checking the rest of the points. And upon completing this algorithm, the target locator will then send the potential list of points to the Pathfinder module. This is a Qt client that was created to help debug some simulations and perform tests on algorithms that will be utilized on the pick. And so with this client, if we switch over to simulation mode, we can draw in objects. As you can see, let's just add a couple more. And then with the arrow keys, we can drive around our rover. And in the bottom left-hand corner, you can see the rover. The blue dots represent sensors, and the red dotted lines represents the range of the sensors. And so if we turn left, you can see that it's starting to update the occupancy grid using this histogrammic in-motion mapping. And so as described earlier, what we're doing is we're using that same algorithm for all of these 5 different sensors. And if we drive around, start turning more, you can eventually, through multiple iterations, you should be able to see an outline for the objects that are on the map. And so if we go over here, hide the objects, you can see that it's starting to create a boundary box for the objects that we see. And as another feature that was later added to help debug what's happening on the pick side, client was enabled to communicate with the pick, and so that this way the client can request the occupancy grid that the pick thinks it sees. And that way you can kind of debug some potential problems that you might have. These two algorithms in combination allow for this module to be robust and handle any size-shaped arena with different number of obstacles and targets. The occupancy grid approach also enables this module to handle unreliable sensor data. And as a further point of improvement, the interpreting algorithm that was described earlier can be improved to become more efficient.
The really interesting thing about the path movement module is that it is solely reliant on the communication from other modules. It has no sensors other than feedback from the wheel motors indicating the rate of their turning. This is really helpful in the robustness to component failure. If communication is down on either end of the rover, it can either wait for accurate information or continue moving based on old, less time-critical target locations. The real trick to being able to develop and test such a device was creating simulators to interact with. We created a highly configurable all-purpose simulator that could request any set of data or respond to any request with a predefined or adjustable message. Here you can see the target gripper version of this simulator responding with alignment information. A user can modify the responses using the GUI and make sure the pick is reacting appropriately. Using data from the target locator and some calculations, we could tell which points were walkable and therefore could be added to the movement lists. With this information, we could use A*, a heuristic of Dijkstra's algorithm, to determine where to go. This algorithm gave us sets of points 3 inches apart that our rover could use to get to its destination while avoiding obstacles and staying inside the map. To do this while maintaining knowledge of the rover's own location, we decided to use PID control and specific profiled movements. With a PID control algorithm, we can set a specific speed for the motors, and using feedback from them and some simple calculations, you can stay somewhere near that set point. For reliable movement, we created a series of set points which could be ramped up, kept constant, then slowed down. These became our profiled movements through tuning of the PID constants and set points. Movement then became reliable and consistent with some limitations. The main limitation of this implementation was the inability to calibrate location over time. This prevented us from removing many targets because the error in the rover's location and angle would build up over time. To add reliability, one large improvement would be to decrease the stoppage and turning. Both of these can be done by researching new movement algorithms and possibly profiling new movements.
Hi, I'm Chris Cox. My role on the team consisted of designing a target grabber module. This module is written in C on a Max32 PIC board. The target grabber is responsible for aligning and acquiring targets when the pathfinding movement module believes it is within 6 inches of a target. The target grabber must be able to detect targets and obstacles as well as differentiate between the two. After multiple revisions, I decided to use 5 short-range sharp IR sensors. I mounted the sensors such that any consecutive 3 sensors have the exact same width as a target. 5 consecutive sensors have the exact same width as an obstacle. This proved to be a great design decision to help with filtering between obstacles and targets. Working with the Lynx Motion Gripper proved to be a great design decision because it allowed a slight bit of error when grabbing a target. I designed this Qt client to simulate the pathfinding movement module. IR values will appear below each designated IR sensor. While this is happening, there is a counter to see how many times each sensor has been read. Simulate the pathfinding movement module. I can send a proximity string, which can be any value the Pathfinder wants to send. However, my pick is only concerned with values closer than 6 inches. Pathfinder also sends when it is stopped and when it is outside the arena to drop a target. Pathfinder can request from the target grabber alignments and if it currently has a target in its gripper. Lastly, displayed in larger text are values for the Pathfinder's movement algorithm. These include projected degrees to turn and the distance from the rover to the target. Ideally, the targets would always be perfectly aligned like the drawing on the left. Here I can easily calculate theta and the distance to the target using trigonometry. A more involved solution, like the drawing on the right, consists of taking both extremes of where a target or obstacle could potentially be and then estimating to the middle of that object. This is because there is a slight gap between the sensors where the object could float from one extreme to the other. From there I would calculate the degrees to turn and the distance to the object, same as before. This is the final revision of the rover with all the sensors mounted. I desoldered the headers from the sensors and then soldered wires directly to the sensors to allow them to be placed as close as possible. I designed the targets such that they are 1.5 inch squares. However, they are multi-layered as you can see here. The first layer is 3 inches tall as this gives plenty of room for my sensors and the sensors on the other rover to verify the target. The second layer is 1.25 inches and this is for the gripper to grab the target. The targets were cut out of foam and I chose foam because it was light, slightly compressible, and could easily be shaped. This shows the 2-layered target with the sensors and gripper. Here you can see the distinct multi-layered aspect and why it was needed. I designed the software filters such that I check each sensor value and see if that value is possible. For example, I know that it is not possible for only IR2 to give a value. Therefore, the sensor gave an incorrect reading and that reading must be filtered out. The other type of filtering consisted of scenarios like this image. I knew that I first wanted to check the object that was closest to the rover. Once I determined what that object was, then I moved on to aligning to the next object. This is our final video demonstration. Here you can see the target locator and searcher and mover modules mapping the target to the arena. Once the target is discovered, rover 1 moves to the edge of the arena and sends a newly mapped arena to rover 2. Rover 2 consists of the target grabber and pathfinder modules. Rover 2 is using an A-star-like algorithm to get within 6 inches of a target. As you can see, we only have one target in the arena. This was due to an accumulation of rover orientation error for rover 2. Rover 2 is precisely finding its way to the target. Now that it is within 6 inches, it grabs the target. Here you can see the target was broken by the gripper, although the gripper still has a piece of the target and is now exiting the map to drop it off. This concludes our final demo video.